So the take-home message I'd like you to get from our investigation of astronomical scale in the last section is that the kind of close inspection we've made of Mars and that we hope to make of Europa is impossible for any object outside our solar system. They're just too far away. We'll have to take a different approach, searching for evidence that can travel to us over the vastest distances of interstellar space. This motivates a new strategy that came in about 1960 to be called SETI, the Search for Extraterrestrial Intelligence. In some ways, SETI resembles that 60s icon, Star Trek, galactic in scope and focused on extraterrestrial life that is essentially like us, intelligent. And because this is astronomy, the definition of intelligence is very specific, broadcasting radio signals. The motivation is as practical as it is chauvinistic. Unless it broadcast, how could we find it? For unlike Star Trek, SETI boldly goes nowhere. SETI waits for the signal to come to us. By 1960, the technology was in place. Radio is the efficient wave band, and astronomers calculated that if technologically advanced alien neighbors emitted radio signals, our telescopes could detect them. Frank Drake, whom you see in the picture, inaugurated the search at the National Radio Astronomy Observatory in Greenbank, West Virginia. Drake's was the first of a series of SETI projects continuing to this day. To date, none have detected any signal bearing clear marks of extraterrestrial intelligence. For example, in the summer of 2022, the giant new Chinese telescope called the 500-meter Aperture Spherical Radio Telescope, or FAST, it caused a flutter of excitement when it detected a signal that was so narrow in waveband that it isn't the kind of thing we think nature makes. But almost as soon as it was announced, and I mean within maybe 2 days, the FAST signal was dismissed as interference from a human source, an unknown human source, but some sort of a human source. So we have been listening with ever better technology for 60 years, and we still haven't gotten an alien message. Does the silence mean there are no aliens? We don't know. We don't know if we're listening to the right channel, and we have no idea of how long it might be reasonable for us to take to look. We don't know for sure whether we'd recognize an alien signal if it arrived. But in spite of the failure to find a signal, I really want to emphasize that SETI projects are not fringe crazy activities. Nothing done with a 500-meter telescope could be described as fringe. Anything that expensive is a national mandate. SETI projects have attracted and continue to attract well-informed, well-regarded, mainstream creative scientists, deeply respected people, and increasingly sophisticated technology. They remain some of the parts of astronomy, maybe the most important part of astronomy for attracting public attention. It's hard to argue with the fact that if we don't search, we're unlikely to find. So, having looked at some of the technology behind SETI, let's take a little look at the equally important theoretical side of SETI, and that is the Drake equation. Back at the beginning of SETI, Frank Drake, whom we just talked about, set out to list the factors influencing how many civilizations there might be in our galaxy, whose signals we might detect. Some of the factors here are astronomical. How many suitable stars are there? We'll call this number n star, the number of stars. What fraction of those stars have planets? We can call that FP, the fraction with planets. Other factors are broadly biological. For instance, on what fraction of those planets does life evolve? F life. How often does life develop intelligence? Once again, talking about broadcasting radio signals, radio transmission. That's F tech. Since stars and planets and life forms all have finite lifespans, and light has a finite speed, timing also matters. So what fraction are broadcasting from a point in space and a time so that we could detect them now? F now. So if we multiply all those factors together, we get a number that could tell us the number of civilizations that we could detect. And this equation has been described as the Drake equation. I don't think that Drake actually claimed it for himself, but other people have come to call it the Drake equation. And this is a slightly streamlined version. You'll see it in other fancier versions if you look online, but it will work for us. And in some ways, it's actually the most useful outcome of the SETI search, not because it allows us to calculate an answer, but because it's a powerful tool to help us think about uncertainty. Think about that for just a second. We often assume that if you can put something in an equation, the point is to calculate it, accurately. Some equations, and this is one of them, are really there to help you organize your knowledge, in this case, to help us think about uncertainty. So for most of the half century since Drake started work, N star was the only term of all of these 5 terms that we knew better than a complete guess. But since there are probably 5 or 10 billion sun-like stars in our galaxy, then all the other numbers can be small fractions. And it's still true that the number of potentially detectable civilizations would be very large. And specifying sun-like limits us to considering stars with the longevity and brightness of our sun. If dimmer, longer-lived stars could also host habitable planets, and astronomers seem to be moving towards at least a qualified acceptance of that idea, N star could be 100 billion. So the other numbers could be pretty tiny fractions indeed. Let's think for a minute about another term there, F now. Sustainability is at the heart of F now. If the typical lifespan of a technological civilization is short, there won't be many civilizations hanging around for conversation. Conversely, if the universe is full of intelligent life, it tells us that civilizations can learn to endure. Remember, I suggested this to you a little while ago when we first asked the question, are we alone? Well, the presence or absence of life out there in the universe is not an absolute prediction about our fate here on Earth. Nonetheless, it's hard not to see this as a pretty significant omen for us. If we collect evidence that other ecosystems exist, then whether or not they survive the development of intelligence may either be a hopeful sign or a deep warning about whether we here on Earth might do the same. So the rest of this talk, the rest of this set of lectures, is really about FP, the fraction of stars with habitable planets. It's obviously kind of hard to tell from these distances whether a planet is habitable. But by this, what we really mean in practice is, and of course, before we go on, let's remind ourselves, by habitable, we mean Earth-like. So what makes a planet Earth-like? Since it's hard to tell from a distance, really the things on which we're going to focus are all about its size and about its distance from its host star. And because all life on Earth requires liquid water, and water is only liquid between the temperatures at which it freezes or melts and the temperature at which it boils, we define a habitable zone as a region around a star on which a planet's surface could lie between the freezing and the boiling point of water. For our sun, the habitable zone includes the orbits of Earth and Mars, and that depends on the strength of the planet's greenhouse effect. For a smaller, dimmer star, the habitable zone will be closer in. That's an easy one to think about. Think if you were out barbecuing or camping and you had a fire, and if it's a small fire, you can get close up. But if it's a big fire, you would need to stay far away so you don't get roasted. But temperature of the star alone, so for a smaller, dimmer star, the habitable zone would be closer in, but temperature of the star alone doesn't make a planet habitable. To offer living conditions in any way like Earth, a planet would also have to be approximately Earth size. And to see why, in the next lecture, we're going to look a little closer at the categories of planets that we recognize in our solar system.